Hello all, welcome to the second week. I hope you enjoyed the lectures of the first week, and I also hope that you have been doing the assignments. So it's a small programming small assignment for the first week, uh, uh, 14 questions or so. So take that seriously, however simple they are. It's good that for you to go and try it and get it working and actually put your solutions back online, so that you can, when you go to the second week and so on, it will be better for you. So in this week we are going to see a few more topics related to taking a Boolean function, how to specify it, how to minimize it and so on. The first of these modules is about universality, and in the second part of this module we will go and look at truth tables and what the truth tables really mean. So let us start with the first one. So I want to give a quick summary of what the basic digital logic gates are. So what you are seeing here is the symbols that you are already aware of: and, or, and XOR, and for and the dot is implicit, so that is removed here. There is x plus y is or, and for XOR we use this symbol where we have a plus and a circle around it, so that is called XOR. So what we are seeing here is you are seeing the name, the symbol that is used commonly, what is the algebraic function for it, and the truth table for it. So it is just a one slide summary of what we have seen already. Now in this one, what we are going to have is the same set of logic functions that we had last time in the previous slide, except that there is also an inversion at the output. So if you notice this is the NOT gate, this is called the NAND gate. So in the NAND gate we have AND followed by an inverter, that is called NAND, OR followed by an inverter is called NOR, and the XOR followed by inverter is called XNOR. So instead of having a symbol which is AND followed by the inverter, typically we use the shortcut where we put a bubble. So you see this circle here, this circle here is attached to the output of the gate. So it is AND gate followed by a small bubble, which is interpreted as NAND or the logical complement of AND. Similarly, OR gate followed by a bubble is seen as complement of OR, and bubble after XOR is XNOR. So this is X XOR Y, the complement, and there is a shortcut notation for XNOR also, which is a dot and a circle around it. So a plus and a circle around it is called XOR, and a dot and a circle around it is called XNOR. You can see that XNOR is a Boolean function which actually checks equivalence of two inputs. So you can see the truth table on the right side. If both the inputs are the same, so 0 0 and 1 1, then the output is 1. If the inputs are different, then the output is 0. So because of this, XNOR is also is essentially checking equivalence of two input bits. So x and y, if they are equal, then f is 1. If they are not equal, then the output is 0. So this is a shortcut notation. So just keep in mind that NAND is just not of AND. So you will see a and then an inversion or a small bubble. NOR is not of OR, so OR gate followed by a bubble and so on. Instead of drawing the OR gate and an inverter explicitly, we will have a shortcut notation where there is a NOR followed by this. In fact, physically, if you go and realize these things, sometimes you can implement these gates directly. The uncomplemented version, namely the and OR, actually needs an inverter after the NOR. So physical implementation in CMOS, for instance, it is a technology used to make chips. In CMOS technology, NAND and NOR are something that you realize with basic transistors with 4 transistors for 2 inputs, and if you want AND, you actually put an inverter following NOR or following NAND to get OR and AND. Anyway, those are details that we can get into later. As of now, just remember the symbols. So NOR is a gate and NAND is a gate, and it is the inversion of the basic gates that we have seen already. So let us look at what is an AND OR circuit. It is the basic kind of a circuit. It is the simplest combinational circuit that you can design. So if you want to design a circuit using AND OR and inverters, all you have to do is you take the Boolean function and express that in the SOP form, let us say the sum of product form, and you may want complemented inputs also. So if you want complemented inputs, you take those literals by taking the variables and putting an inverter to get the complemented literals. then you form the product terms using AND gates, because each is a product, then you can actually use an AND gate to get the product, and the logical sum that you need for all of those is achieved using a OR gate. That's why it's called a AND OR circuit. So the process is, you start with an SOP has various product terms which may have complemented and uncomplemented literals. Wherever you have complemented literals, use inverters and connect them using AND gate, and you have various product terms now, connect them using a OR gate, you have a AND OR circuit. So let us look at this small example here. F of xyz is xy plus x bar into yz, and this is already in the sum of products form. So this is a product term, this is a product term, and you need a sum for that, it is already in the sum of product form. Then if you want to realize it, you can do it this way. So you look at this AND gate, this is doing x and y, and if you look at this AND gate, it is taking x and complementing it. So this line is x bar, then you have y and z, so this is x bar yz. So you have all the product terms ready by now, and finally there is a single OR gate which is doing this logical sum. So you have that here. So this is a basic AND OR circuit. So I would like you to go and implement the function f of xyz as x plus y complement and y plus z complement and x plus x complement using OR AND logic. So in OR AND logic, what you do is, these are all product terms. So these are all, this is a product of some terms, I am sorry, this is a product of some terms. You take each of these sums and implement that using OR. So you may also want to use inverters before you do the logical OR, and finally you have 3 sum terms, you want a product of that, you use the AND logic for that. So go and try this out, it is very similar to doing this, except that you will have first you will have a set of OR gates and then you will have a AND gate. So in this circuit what we have is a direct implementation of xy plus x bar yz. We did not try to simplify it or do anything else, this is directly writing it in this form. So it is just to show you that AND OR circuit is easy to arrive at. So now let us get into this concept of universality. So sometimes what happens is, let us say you know that basic AND, OR and NOT are the logical operations that are there in Boolean logic. So therefore if you have only AND, OR and NOT gates, it is enough to implement any circuit technically. So if I give you an infinite supply of AND gates, OR gates and NOT gates, you can implement any Boolean function with only these things. So there is this notion of universality, where I call a gate as universal if it can implement any Boolean function without the need of any other type of the gate. So if I look at AND gate alone, right, AND gate by itself is not universal, because you cannot implement OR operations and NOT operation by only using an AND gate. However, NAND and NOR are called universal gates. So these are called universal because even if you do not have any other type of gate, as long as you have just the NAND gates or just the NOR gates, it is enough to implement any Boolean function. So in general, if you want to show if a gate is universal or not, all we have to show is, using NAND alone, let us say, we should be able to get AND, OR and NOT operations implemented. Similarly, just using NOR alone, if you are able to get AND, OR and NOT operations implemented, then these two gates can be called as universal gates. So again, to reiterate, universal gate is one in which you can implement the 3 basic Boolean functions, namely AND, OR and NOT, without using any other type of gates. So let us see how this can be done. I will show you the example for how to show universality of the NAND gate. So I want to show that AND, OR and NOT can all be implemented using only NAND. So let us start with NOT. If you want to do NOT, so this is an implementation where I use a single NAND gate and get complement of input. So I have X which is given to both the inputs, and what is the logical operation in terms of NAND? It takes the 2 inputs and ANDs it and complements the resulting product. So we have the product, in this case X is connected to both the inputs, so it is X and X, the complement of that, X and X is X itself, so you can see this is X complement. So what this circuit is doing with this connection here is actually implementing inverter. Then let us look at AND. So AND we know is not of NAND. So NAND is not of AND. So essentially AND is the not of NAND also. So if you want to get X and Y, what we can then do is take a NAND that gives me X and Y complement. Now we have the complemented version of the output that we are expecting, send that to an inverter, right. So F is the inputs complement, because remember this is the circuit for a NOT gate, right, we just saw it a while ago, this is the circuit for a NOT gate. So it takes whatever input is coming in and complements it, and what is the input that is coming in for F, it is P, which is XY complement. So XY complements complement is, so we know that A bar bar is A itself, so XY complement complement is XY itself. So we have shown that OR and, so we have shown that NOT and AND can be done using only NAND. Finally, if we want to show OR operation, it is slightly more involved, but here it actually uses De Morgan's theorem. So what it does is, you take X and Y as inputs, you complement the inputs. If you complement the inputs and send it to a NAND gate, it gives you X plus Y. Let us see how. So you take this line, this is X followed by an inverter here, this is the inversion operation. So this line will be X bar and this line will be Y bar, and what is the NAND doing? It will do X bar and Y bar, the complement of that. So if you take De Morgan's theorem, this is complement of the product is the same as sum of the complements. So you take X complement is the term here, Y complement is the term here, so that is what you have here, and this complement and this dot using De Morgan's theorem will essentially come as the logical OR here and the complements to the inputs to that gate, which is X bar and Y bar, and we know that X bar bar is X, Y bar bar is Y, and this essentially gives us as a black box. If you look at this boundary, right, so if I draw a boundary here with X and Y as input and F as output, this will give me a OR gate. So the reason why this universality is interesting is that if I am given just NAND gates, you can implement this circuit. As long as I can do AND, OR and NOT, I will be able to implement any circuit. So what I would like you to do is go and think about whether NOR is a universal gate, and if it is so, show that it is actually a universal gate. So you have to use a process which is very similar to what I did earlier. So in fact I will give this to you, NOR gate is actually universal. I would like you to go and show that it is universal by appropriately combining the Boolean functions. See if you can get AND, OR and NOT operation only using NOR gates. So the other thing that I want you to think about is XOR a universal gate? So if XOR is a universal gate, you should be implement OR, NOT and AND only using XOR gates, nothing else. So if you think that it is a universal gate, show how each of these operations can be done using XOR gates only. If you think it is not, at least think about which operations can be done using XOR only and which cannot be. Go and in some sense think about why, if the second one is the case, see why it happens also. If first one is the case, you have to give a circuit which actually shows this. So do this as your mental exercise. So now let us switch to something else. So we are going to look at how to go from Boolean expressions to truth tables and how to go from truth tables back to Boolean expressions. So if you want to convert a Boolean expression to truth table, it is relatively easy. So what we want, so there are several ways in which you can do it. I will show you one way in which it can be done. So in this example, f of x y z is z bar plus yz. If you are given something like this, and let us say I want to implement this function, remember this is z bar plus yz, it is not a function of x. If you notice, it is not a function of x. In fact, this can be simplified a little further, but let us start with this Boolean function now. Let us say I gave you this function, I want you to fill up the truth table for it, and I am asking the truth table to be of 3 inputs, which means you need 8 rows and 4 columns. So that is what we have here. We have a function x y z, 3 inputs, so there are 8 different input combinations, and f is a function of x y z. So I am given this function, I want to fill up this truth table. Let us see how to do it. So first we take z bar. So what that means is, so this is a sum of products, right? So I will take each of the product terms. So the first product term is just a simple literal z bar, and if I want to see what is the contribution of this to the truth table, what it says is whenever z is 0, this expression is 0 complement plus yz, which is same as 1 plus yz, which is the same as 1, which means if z is 0, f becomes 1. So what we can then do is wherever you see z equals 0, put f equals 1, because that is what this function says. If z is 0, 0 complement plus yz is 1 plus yz, which is same as 1. So wherever z is 0, you put a 1, right. So there are 4 places where z will be a 0, this row, this row, this row and this row. So that takes care of z bar. Now let us go and look at yz. So yz, if this term becomes 1, then z bar plus 1 will be 1. So if both y and z are 1, f will become 1. Let us go and look at the rows where both y and z are 1. So in this row both y and z are 1, and in the last row y and z are 1. So you have marked that. Now we have exhausted all the product terms, which means all the entries that we need to put in are already taken care of. We do not need to do anything more. So whatever is remaining must be zeros. So these two are essentially zeros. So this is one way to fill up the truth table. Another way to do that, which is slightly more explicit, is get the min terms that are involved in it. So the way to do that is you take z bar, we have seen these expressions before. So this is missing a x term, so express it in terms of x. So z bar into x bar plus x plus yz. Then this is essentially a rearrangement, x bar z bar plus yz plus xz bar. Now if you look at each of these terms, this term is missing a y, so we introduce y. This term is missing a x, so we introduce something in terms of x. This is missing a z, so we introduce something in terms of z. Sorry, this is missing a y, so we introduce something in terms of y. That gives us these 6 terms. And if you look at these 6 terms, so x bar, y, z bar, so this is 0, 1, 0, that is the same as 2. Then you have 0, 0, 0, that is 0. Then 1, 1, 1 is 7. Then 0, 1, 1 is 3, and so on. So this gives us 6 min terms, 0, 2, 3, 4, 6 and 7. If you go and look at this truth table here, so the row containing 0, 0, 0, the row containing 0, 1, 0, the row containing 0, 1, 1 and so on will be 1s. The row containing min term 1 and min term 5 should contain zeros. We can verify that. So the row containing min term 1 is this row, and row containing min term 5 is this row. These have zeros in them. So if you want to go from the other way around, given a truth table, get to a Boolean expression, this is slightly more complicated. So what you should usually do is write a canonical sum of product expression and simplify the expression. For example, if I give you something like this, this is the same thing as what we had earlier, 0, 2, 3, 4, 6, 7. You go and write, so this is a canonical sum of product, it has min terms. Now you go and write it as an algebraic expression involving x, y and z. So each one of these terms corresponds to one term from here in the same order. Then you start applying some simplification logic, whatever rules that we have seen so far, you apply that sequence of simplifications, you end up with something like this, z bar plus yz. So starting from an expression, so starting from a CSOP, a canonical sum of product, so this is essentially a truth table, right. So it says that 0th row, the second row and third row and so on, the row containing min term 0, min term 2, min term 3 and so on are all ones. So we have taken that and derived a much simpler Boolean expression. So this is the process that we have seen in the last week, and it is quite complicated because you have to remember all the rules and so on, it gets a bit messy. Let us see if there is a way to simplify that. So when the expressions get more complicated, this Boolean simplification gets very hard, and you may actually miss out some of these things, and you may end up with something which is complicated. Also, more the number of inputs that is given, you have to put in more and more effort. So we want to have a systematic way of reducing this effort, and in the next module we will go and look at what are called Karnaugh maps, which do exactly that. So before we get into Karnaugh maps, let us see what these truth tables are. So let us start with the same function here, x, y and z, and this is my function f, that is necessary. So, the first thing I am going to do is, instead of saying x, y and z, I am going to say these are the min terms, and I preserve the order in the output. So, f of x, y, z. So, I know that the order of the inputs is x, y and z, because that is the order in the left to right. So, I know the min terms now, but what about the min terms? We know that 0 0 0 corresponds to min term 0, 1 1 1 corresponds to min term 7 and so on. So, essentially for min term 0, if min term 0, if this product term becomes 1, f becomes 1, for if this product term becomes 1, the output is still 0 and so on, right. So, there are, so you can see the correspondence between the table here on the left and the table in the middle. Now, let us see if this can be rearranged differently. So, the first thing I am going to do is, instead of writing it as 8 different rows and 2 columns, I am going to rearrange it a little bit. So, I have 3 rows here and 5 columns, but the truth table is actually in this, in the last 4 columns and in the bottom 2 rows, wherever you see zeros and ones. So, let us see what this means. So, the first thing is, let us go and look at what is here. It says x is the representative for the columns here, and all combinations of y z are represented in this row here. So, there are 4 columns representing the 4 combinations of y and z, and there are 2 rows which are representing the 2 combinations of x. So, if you notice the order, x can take 0 or 1 and y z can take 0 0, 0 1, 1 0 or 1 1. In some sense, what we have done is, we have taken this and folded it, folded this table into something like this. So, let us see what the entries are. So, when x is 0, it is these top 4 rows here, right, these top 4 rows. If you look at the entries here, it is 1 0, 1 and 1, that is what you have here, 1 0, 1 and 1. Similarly, when x is 1 here, you have y and z as 0 0 0 1, 1 0 1 1, for those the output should be 1 0 1 1. So, that is what you have here, 1 0 1 and 1. So, if I pick this, it corresponds to the term x equals 0, y equals 0 and z equals 1, or this is min term 1. If I pick this term here, this corresponds to x equals 1, y equals 1 and z equals 0, or this is for min term 6. All I have done is, I have taken this table here and folded that in a slightly different way. Now, I am going to take this and do something more. What I am going to do here is, I will keep the row order as it is, but I am going to shuffle the order of the columns. So, I have 1 1 here, this column 1 1 contains 2 ones, I am going to bring that here. This column 1 0 contains 1 1, I am going to bring that here. So, the ordering is slightly different here. In x, it can take values zeros and 1, and y z is going to take the value 0 0 or 0 1 or 1 1 or 1 0. We have not lost anything from the truth table here. You pick any term here, you go back and check those entries in the rows here, they are still the same. All we have done is taken this table, folded it in a different form and then rearranged the columns, and we are here now. So, for 3 input functions, we are going to rearrange the tables in this form. We will see the reason why we are doing this form as opposed to this or this. So, we get to do something interesting the moment you write the truth table in this form. We will see that in the next lecture. So, in general, what we have is, we have let us say it is a function of 3 inputs that we want to look at. The inputs, let us say, are x1, x2 and x3, then you rearrange them in this form, namely 0 0 0 1, 1 1 and 1 0. It is clear that if we read from x1 to x2 x3, this is 0 followed by 0 0, so that is 0 0 0, 1 followed by 0 0, that is 1 0 0 and so on. So, this will give us min term 0, this is supposed to be min term 4, m001 is min term 1 and this is m5 and so on. So, this is min term 0, 1, 3 and 2, and this row contains min term 4, 5, 7 and 6. So, given a truth table, without going through this folding and other things, you can directly come to this one. We will see why this is useful in the next module. So, this brings me to end of this module. What we have seen in this module is universality of NAND and NOR gates, and we also saw how to rearrange the tables and so on to set up the platform for what is called Karnaugh maps. We will do that in the next lecture. Thank you.